Hey friends, it's good to be back with you. Today I'd like to finish up derivatives before we move on to integrals. In particular, I want to talk a little bit about numerical derivatives, finite difference derivatives. Before we do that, I want to make sure we've got the product rule and the chain rule figured out. Now, this is the definition for a derivative. This is what emerged in the late 1600s, I guess, from Newton and Leibniz and maybe a couple others. Now, dy dx and y prime mean the same thing. We've got two different notations for the same thing. Why two notations? I don't know. How many people helped develop calculus? Not everybody wrote things down in the same way, and here we are. Okay, this part right here, that is the definition of slope of a straight line. That's all that is. This thing right here, this limit, this is what turns algebra into calculus. Now, if this delta x approaching 0 but never quite getting there, this idea of the infinitesimal is still causing you some trouble, that's okay. It does to most people. I don't want you to think that we're somehow winging this or this is some kind of fuzzy idea. This idea right here, in particular, as described using infinitesimals, sits on a very firm foundation of rigorous mathematical proof. There's no guessing about this. Mathematicians know exactly what this is, and they know exactly how to handle it. So don't think we're winging it here. We're on solid ground here. Now, it's easy enough if you, in the example I did before, we said, well, what if y equals x squared? Well, we plugged x squared in there, and we got 2x for the derivative. No problem. Well, that's kind of simple. What happens if we get something more complicated than that? We need some more sort of general rule, because we can't keep plugging complicated functions into this and doing all the manipulation it takes to get the answer. There are two general rules for derivatives that you're going to use all the time when you're working with math. So let me erase this. The first one is called the product rule. And all that means is what happens if you have a function that's just multiplied the product of two other functions. So a mathematician might say, well, f of x equals ax times bx. What's that? Okay, let's try this. Here's an example. What if ax is x squared and bx is sine x? Okay, hang on, let me make a better 2, there we go. Now, that's a function that's just the product of two other functions. A of x equals x squared, b of x equals sine x. So, the derivative with respect to x, and let's see, let me write this down here. That looks better. Equals just the derivative of the first times the second plus the derivative of the second times the first. That's easy to write. In fact, let me write it down here first. Okay. Derivative of the first times the second plus the derivative of the second times the first. Well, how do we know this? Well, because somebody, a long time ago, plugged ax times bx into the expression for the derivative, and this is what came out. So in practice, how do we calculate with this? Well, let's find the derivative of that. Okay, derivative of the first times the second. Well, so d f dx, where that's f right there. Derivative of the first times the second. Well, I can do that. Times the second, which is sine x, plus the derivative of the second times the first. Well, the derivative of sine is cosine, so it's x squared cosine x. That's so easy a professor can do it. So you know what that's got to be like. So that's the product rule. There's nothing more to it than that. You'll come across functions that are of this form, ax times bx, but look pretty involved. But once you realize you can break them down into the product of two, it's no problem. Just follow this rule and you can find the derivative. So the next thing we need to learn about is called the chain rule. And let me erase my board here. Now what if we have a function that's a little more insidious than just the product of two other functions? Okay, let's start with this one. Y equals e to the x squared. Well, That part's easy to write down. If you work with statistics a lot, you'll notice that's not too far removed from a normal distribution, so you'll see things like this regularly. Well, how do you do this? You need the chain rule. Chain rule says this. What if I have a function that's f of u, where u is a function of x? Well, that's what this is. What if I could write this as y equals e to the u, where u of x equals x squared. That's okay. Well, the chain rule is very, very simple. In this case, I can say dy with respect to x is a derivative with y with respect to u times the derivative of u with respect to x. Now, basically what's going on in practice, I don't want to be too cavalier about this, but basically those are canceling out as would any other variable. Because remember, these are variables. dy, dx, those are variables. Now you can push them around like any other variable. They have some unique properties, but if you want to think of them as variables, it's okay to do that as long as you're careful about it. So that's the chain rule. Well, how am I going to apply that here? Let's try this. All right. So dy dx equals dy du times du dx. Okay, well, what's that mean? Well, dy du, well, what's the derivative of e to the u with respect to the u? Conveniently, it's e to the u. Okay, that's e to the u, because e to the x is its own derivative. It's the only function that is its own derivative. And what's du times du dx? Well, du dx, that's just 2x, isn't it? Well, let's see. Let's plug u back in there. So e to the, in fact, let's reverse order too, just to keep this from getting hard to read. Okay, and that's the derivative with respect to, I'm going to check what I'm doing is I'm checking my screen over there. I've got it on my screen. I want to make sure I get it right before I move on. But that is correct. That's the chain rule. So those are the two rules you're going to use. Now there's another one called the quotient rule. And quotient rule is just what it sounds like. What if you have a function, what if f of x equals a of x over bx? Also happens all the time. Well, there's a separate rule for that if you want, but a more straightforward way to do it, if you ask me, is just to say that f of x equals a of x, b of x to the minus 1, and just use the product rule again. Now, 1,000 years ago when I was in undergraduate school, I decided it was too hard to remember the quotient rule. So I just started doing this, and it works fine. I've been getting correct answers on this ever since, so I guess it must be okay. Now, with that out of the way, let's move on to finite differences. And in particular, I want to describe the 2 or 3 different kinds of finite differences you're going to see if you do a lot of numerical methods. So let me start by erasing my board. And let's remind ourselves what a finite difference derivative is. Let's go back to, well, that was terrible. I guess it's okay. So there's x and y right there. And I've got some function. What does the function mean? Well, it's something we care about. It may be lift as a function of velocity, or it may be the amount of gas my car burns, or something. It could be anything that we, physical that we care about. And let's say it looks like this, all right? And I'll call that y of x, perhaps. Now, if I want to know where the slope is in any one place, I'm going to do this. Say that I'm going to call that x of n and x of n plus 1. That's y of n and y of n plus 1. Okay, we've seen this before. Now, real quick, why would I want to know the slope of something? Well, I think I mentioned this before, that a differential equation is just an equation that has a slope in it. As far as I can tell, almost all physical laws are written in terms of differential equations. That means all physical laws, all the ones I can think of, have slopes in them. So we care very, very much. What's a simple example? Well, let's look at Newton's law. Now, Newton wrote we say F equals ma. That's not actually what he wrote. He wrote F equals m times the time derivative of velocity, which is acceleration. So slopes are built right into Newton's law, which is about the simplest law there is. And if we know position and we want to find velocity, that's a derivative. If we want to find we know velocity and we want to find acceleration, that's a derivative. All right? They're just cooked into everything we do. So derivatives are absolutely everywhere. We have plenty of good, practical, immediate, compelling reasons to want to know what they are. All right? So let's just make this red maybe. I'm going to figure out the slope of that line right there. When we looked at the definition of a derivative, we let that go to an infinitesimally small number. It approached zero without actually getting to zero. Now, when you're working with numerical methods, you can't have infinitesimals. You must know what every number is. So what if we do it this way? What if we say dy dx is approximately y of x of n plus delta x or y of n plus 1 minus y of n over delta x, all right? If this is a number and we know what this is, okay, big idea here. This is a number. We know what it is. It's not an infinitesimal anymore. Now, is that exactly the derivative? No, it's not. Is it close? Depends on how big that is. Can we make delta x very, very small, but known? Yes, of course we can. Right? And so that's a finite difference derivative. We've talked about that before. Now, let's get into the details a little bit of how exactly we're going to do this. The way I did this, I assumed we were right here. Maybe we're stepping forward in space or stepping forward in time, and we're right there and trying to figure out where that is. Okay? And so I looked forward, so I said, I'm looking forward from where I am to where I want to go, to the next step, and I'm using that to define the derivative. Well, this is called, unsurprisingly, whoops, messed that up, didn't I? This is called a forward difference. It's a forward difference, okay, where I'm right here, I'm looking forward to see where I'm going to go next. Forward difference. So when I calculate the derivative, I reach forward in space or time to find the next point. Well, that's fine for a derivative. What about a second derivative? Could you do that with finite differences? Sure. Once again, let me erase my little board here. And let's stick with the idea of the forward difference here. Well, what would a second derivative look like? Let's just say y double prime. That's a second derivative. If you prefer to write it out this way, you can. They mean the same thing, so suit yourself. Well, let's see. That would be like y prime of n plus 1 minus y prime of n. All right. Second derivative is just a derivative of a derivative, right? Well, okay. Let's break this out. What is y prime at n? Well, we know that if we're going to use a forward difference, we're going to use what I just erased there, and I'm going to say y of n plus 1 minus y of n over delta x. All right, that sounds pretty good. Well, what would y prime at n plus 1 look like? Well, looks to me like I'm probably just going to increase the indexes here and here, and I'm going to write it down again. So let's do that. All right, so far so good. Well, now what? Well, let's plug this in there and that in there, and let's see what happens. All right, so y double prime must be Can we see that there? Okay, good. So what I've done here, took this expression for y prime of n, put it there, and y prime of n plus 1, put it there, and just I'm going to substitute it in. Let's just clean this up a little bit. Now, looks like doesn't it look like I got delta x in too many places? I don't. Remember, delta x is the derivative there, or the denominator there and there. But those are up here. There's still another one there. That's the other delta x. So I'm not getting my bookkeeping messed up here. If you work this out, okay, there's the second forward difference. No problem. Well, I keep saying forward difference. Is there such a thing as a backward difference? Sure. And it's just what you think it is. I'm going to erase my board again and write this down real quick before we move on to MATLAB. Okay, so backwards difference is, I'm going to take this same idea of looking at a curve where that's x and y, just like I did before. I'm going to call that x of n, and I'm going to call that x of n minus 1. That's y of n minus 1, and that's y of n. Really? Yeah, really. This is really what it is. All right, let's just do this here. It's y of n. That's all it is, with this being delta x in here. Just reasons of completeness, let's just write that in there. Well, that doesn't seem that much different, does it? All I did was just subtract 1 from the index numbers. It seems like this, I'm just playing bookkeeping games here. Well, for right now, you can think that, and it's probably not too far off. What'll happen here in the next, I don't know, few weeks, I guess, as we start looking at finite difference solutions to differential equations, the idea of a forward difference and the idea of a backward difference become very important. They behave differently in certain conditions. And if you've ever seen the words an implicit or explicit solution to a differential equation, explicit is forward difference and implicit is backwards difference. It's about that straightforward. So put a bookmark in this one in your brain, and we're going to get back to this one in a little while here. But it's important that you know what a forward difference and a backwards difference is. So with all this in mind, let's take all this and let's go to my computer and see how we're going to grind through this in MATLAB.